meets nature, and fiction becomes fact. Now this may not be the cutest of creatures, and you may not think it's the most appealing thing on which to model a machine. But animals, including cockroaches, are increasingly becoming the inspiration for robot designers. Some scientists believe that not only can we learn from nature, but we can improve on it. Meet the new creatures of the robotic age, the Robocritters. Charlie, you can go for a walk in a minute. For those that believe that robots are pure fiction, the news is that they're already here, working for us, doing the jobs we don't want to do, the 3Ds, the dull, the dirty, and the dangerous. But you ain't seen nothing yet. The next generation of robots is evolving 10 million times faster than biological life. Scientists around the world are building robots with features and behaviours of animals as diverse as insects, snakes, and fish. Some are taking on the greatest challenge of all, making robots as intelligent and versatile as ourselves.
I think we can learn a tremendous amount from the natural world. They're not just from human beings, but there are a wealth of different animal species there, all existing in little niches, and all of those can be very valuable to us as information to use in researching for robotics.
I think that certainly understanding ourselves and understanding nature is a key to progress in understanding how to make lifelike or intelligent robots in the future.
Quite often you gain inspiration from nature. You look at, particularly with robots that move around, nature's found a very good way of doing it very often. And if you look at nature, see what's happened, yeah, maybe we can do it that way too. More often than not, yes, it's successful when you do that.
Nature has many design models for a mobile robocritter, depending on where it will live and what it will do. Most land-based animals like us have legs, but scientists have found that it isn't easy getting robots to walk. Researchers the world over have been struggling with the problem for decades. A champion walker is the spring flamingo at the Leg Lab in Massachusetts. But why not use wheels?
You certainly will never beat a wheel on a smooth road in terms of efficiency, but we think that legs might very well be one of the more efficient ways to get around on rough terrain. We try as hard as we can to make use of whatever nature has figured out over the billions of years of evolution. And so we actually try to replicate the lengths of the links on the limbs themselves, even some of the masses of the different components, and certainly the configuration of the joints. I really love this question of how many legs a robot should have, because most people come to us and they ask the question, well, why should your robot have 2 legs? It might fall over. You better give it 4, or even better, 6. But I think about the question a little bit differently. We have a creature, and it has 4 limbs. We have to ask ourselves, what do we want to do with those 4 limbs? And, well, okay, we could use all 4 of them to walk, but then when the creature got to where it's going, it doesn't have any hands, right? So, well, why don't we allow the creature, if it wants to scamper around on those 4 limbs to transport itself to a destination, and then when it got there to be able to stand up on 2 and use the other 2 limbs to manipulate things and to actually do some work. From there, you ask the question, well, maybe we could walk around on those 2 legs even more of the time. And it turns out that walking around on 2 legs isn't that hard most of the time.
What they've found is that getting a mechanism to walk on the flat isn't that difficult, but getting it to cope with life's unexpected ups and downs is much more of a challenge. At the University of California in Berkeley, Biologists are busy looking at just this problem. Bob Full gives animals a workout in the name of science. He's passing the results on to robot engineers at a company in Boston.
Well, we're called the Polypedal Lab, so we study things with lots of legs. And our basic philosophy is that diversity enables discovery. So what we do is look at a wide diversity of creatures, things like centipedes and insects and crabs, and try to extract from them general principles about how all things move. We've discovered, for example, that even though animals have a number of different designs, different leg numbers, different leg shapes, different body forms, that they all produce the same forces when they push on the ground. And you can model them very simply as a spring mass system or something like a pogo stick. All these different creatures, even though they look so different, are bouncing along as they move in a very similar way.
Bob's found that animals with lots of legs have greater stability and maneuverability. Their legs act like springs and shock absorbers, each one wired up to its own mini-brain, so that the animals don't have to think too hard to overcome obstacles. They just keep moving forward, and their legs do most of the work. But according to Bob, there are limits in how far you should copy nature's designs.
We actually say that copying nature is a mistake, because really everyone knows that evolution works on the just good enough principle. So instead, we really propose to look at nature with respect to inspiration. That is, extract the general principles from nature and use those principles from any diverse organism that best illustrates them, and capture those principles and put them into the robot.
And he's looking at animals that don't just walk, but walk up walls. And there's no better or faster wall climber than a gecko. If engineers can create a mecho gecko, it will be able to go places no other robot can reach.
The geckos are an incredible example of basically the theme of the lab, that diversity enables discovery. So if you want to know about climbing, where do? You go to the gecko, because they're spectacular climbers. They're able to run up a wall at nearly a meter per second. And we were really surprised how effective they were in doing so. The way they do it is they have special feet.
Geckos' feet have billions of microscopic hairs which stick using molecular forces. But Bob had another intriguing mystery to solve.
The most interesting thing about them is not that they can stick on the wall well, but actually when they run, how they unstick or detach. And the way they do it is really fascinating. It's very much like what you would do if you put tape on the wall. So if you put a piece of tape on the wall, you wouldn't take that tape off by pulling down on it. What you'd do is you'd peel it nicely. And in fact, that's exactly what the geckos do. They peel their toes away from the surface at these high speeds when they're running, so that their detachment forces are essentially zero. And it's very much for them like running on the level.
Well, Bob's been looking at the geckos, and he's let us know how the geckos move, how they climb, certain ways they transition between the walls, and we've tried to take that information and incorporate it into our robots. The ones you've seen right now are very first stage robots, so we're just looking at how they stick and ways they can stick to the wall and how they can move. But right now we're simply using a reusable adhesive. You know, it's a first crack at it, and hopefully it'll be replaced with the work that Bob is doing on microfabricating the actual gecko adhesion. Right now they're strictly remote controlled. There's no autonomy on right now. In the future, we will be adding a controller to them on board, and they will have either limited autonomy, where you'll control the rough movements with a remote control, and they'll do the fine stepping on the wall, or complete autonomy, where you might let one go in an office building, and it'll try to find the highest, darkest spot in the room and just sit and listen.
So, look out for a mecho gecko spying from a wall near you and other creeping crawlers. This could be your worst nightmare, a huge spider. But they are a great bit of design. They've got a low centre of gravity slung between those 8 legs, which keeps them really stable and strong. And they can climb up vertical surfaces like this log, because they've got claws and hairs on their feet for clinging on. The only snag with that is they're not very good at climbing smooth surfaces, so they're not so good at getting out of your bath. So robot designers at a company in Portsmouth decided to use the spider as a blueprint for a climbing robot to inspect and repair inside ships' hulls or nuclear reactors. The robot uses pneumatic feet to fasten itself in place. Unlike most real spiders, it doesn't have speed on its side, but it is one of the most advanced legged robots in the world, and one you can't squash.
Well, spiders are excellent walkers. We'll never create a robot that's as good as a spider, but if we can get something that approximates it and incorporates some of the aspects of spiders' abilities, then we'll be very happy. See, the robot's really strong. It can carry about 150 kilos, and it only weighs 50 kilos, so that's a really high power-to-weight ratio. And what we're trying to do is get close to the power-to-weight ratio where we get, say, the common garden ant can carry 20 times its own weight. Each actuator joint, i.e. the powered joint, has its own CPU or microprocessor. And what that is a small brain which does all the hard work for us. We tell it where to go and how hard to push, and it does all the hard work. And then between them, they talk to each other and coordinate the legs, so at the end of the day, the foot does what we want it to do. And then we just say to the robot, walk, and all the legs talk to each other, and it works. Unfortunately, compared to what nature is capable of, we've got a long way to go.
Snakes have come up with a radical solution to the leg problem. They don't have any. They lie on the ground and use muscle contractions to push themselves along. It's a surprisingly efficient means of propulsion, and they can get into places other animals can't. Working from his home near San Francisco, Gavin Miller has a passionate hobby: building robot snakes. He's been at it for 10 years. But what's so special about snakes for him?
There are some interesting things about snakes. The first thing is they don't fall over, so you don't need a sense of balance. And when I started, the electronics to enable that were very expensive and fairly heavy and large. And the thing that intrigued me about the snakes is they have a very organic, lively quality, and I thought that that was probably because they have a large number of degrees of freedom. Typically, early robots had a few joints and they looked very mechanical, whereas here we're approximating a sort of sinuous technology which hasn't previously existed. The key feature of this design of snake is the spine, which you see running across the back here. This is made up of universal joints, and they have the quality that they can flex vertically and horizontally, but they resist twisting. And I realized that if I took a series of segments and joined them together using universal joints, then I could mimic the structure of a real snake. And in a real snake, there are a series of muscles that run along the outside which pull on the ribs, and then also between the ribs to make them flex up and down like this. And those are represented by the two radio-controlled servos here and the rods here. And so by having a series of connections like this along the length, I can make each segment bend both vertically and horizontally, and that's how you get sidewinding motion as well as normal locomotion.
Gavin's next goal is to make a snake that's strong enough to climb trees, like some of its wild relatives. A robot like this could be used for search and rescue missions in inaccessible locations like collapsed buildings. Getting into difficult or dangerous locations is the prime function of many robots, and there are few places more dangerous than minefields, especially at sea. The American military need robots to clear mines in the surf zone, so Bob Full suggested modelling them on crabs, the natural occupants of this habitat. They call their amphibious robot Ariel.
Ariel's been in development for about 3.5 years. This is Ariel, and it's a robot designed for mine clearance in the surf zone underwater. And it will probe for mines with sensors that are attached to its legs. One of the advantages of making it move like a crab, which is sideways as opposed to forward, the way an insect does, is that it gives us more legs in line with aerial search path, so we can probe with greater sensitivity.
The aerial project is a good demonstration of how you don't need to copy nature. You can actually make it more difficult if you blindly copy nature. For example, if you look at this leg that we helped IS Robotics design, the animal itself has many more joints than you see in this leg. It has, for example, 9 different joints that can move, or degrees of freedom. What we did is we analyzed the crab, a real actual crab running on the treadmill, and we discovered that in fact many of the joints work together as one. So an animal like a crab is incredibly complex, and if we give all that complexity to engineers, we actually make their tasks more difficult rather than less difficult.
It's not just the joints that can be simplified. Ariel only has 6 legs instead of 10.
More legs than 6 would just give us control complexity that we just don't need. A crab does more with its 10 legs, but the problem is complex enough with 6. We wouldn't gain appreciably anything greater than that. Another slight improvement over a regular crab is that if you flip Ariel over on its back, it will know that it's been inverted and simply swing its legs down in the other direction and continue to walk. Ariel can be run completely autonomously at this point. We can download a mission into it, and it will search an area through the surf zone, sweeping back and forth and probing through the sand for any kind of metal contact.
Imagine, in the future, how effective a swarm of expendable aerials would be, working together to clear minefields. At nearby Northeastern University on the Atlantic seaboard, Professor Joseph Ayers is working on a rival to Ariel. He's more of a lobster man.
Lobsters and I go back a long way. I'm infamous for having eaten almost every experiment that I've done. In fact, I wrote a cookbook about lobsters, and I find them among the more fascinating creatures there are in the ocean. Their robustness in an incredibly changing environment is incredible. Their productivity is amazing in this area. It's the largest industry in this town, in fact, is lobster fishing.
Joseph specializes in studying natural nervous systems and designing artificial ones. And just like a lobster, he seems happiest when he's immersed in water.
It's sort of like my own personal cocoon. I go in there, I'm surrounded with the white noise of the jacuzzi jets. It's a nice warm environment and nobody bothers me. Nobody calls me up and I can work for long hours. And I've just gotten into a practice of getting up very early in the morning and going into my jacuzzi with my computer and doing my programming. And I have to tell you, those are the most productive times of my day. Our idea was that, in fact, that the set of behavioral acts that a lobster goes through when it is searching for food is exactly what you would want a robot to do to look for mines. So if we could embody the behavior and the performance advantages of the lobster in a robot, we would have the ideal robot for that particular task.
Building artificial sensing and control systems is key to the development of robots. Just like a real lobster, his robot will need to be able to sense its environment. A real lobster's antennae feel for obstacles, so will the robot's. And to walk and stay upright, it needs to have sensors in its legs and feet. Of course, there are some things that a robot lobster would be good at, and some they wouldn't.
Mission planning, for example, is something that a lobster doesn't do very well, but humans do extremely well. And so coming up with long-term mission plans, motivation, a real lobster is very hard to motivate to go out and find mines, but we can, in fact, can that idea or that motivation and put it in the robot.
Away from the shoreline, the inhabitants of the deep sea are an obvious inspiration for swimming robots. This undersea exploration robot has been modelled on a dolphin, but its power comes from a propeller instead of flippers and fins. To make it faster and more efficient, designers are looking to copy the way sea creatures actually swim. The ideal models for high-speed underwater robots are tuna and trevallies, swift and tireless predators of the deep. Their muscle-packed bodies create propulsive eddies in the water, helping them to hit speeds of nearly 50 miles an hour. At MIT in Boston, they've been working on a robo-tuna for the past 3 years. They've succeeded in reproducing a tuna's undulating swimming movement using a system of cables and pulleys that bends the robot's spine. At high speeds, minimizing friction with the water is essential, so they're also trying to reproduce the exact body shape. One day, a robo-tuna could be large enough to take passengers, revolutionizing the propulsion of future submarines. But not all fish swim the same way. Pike are freshwater predators designed for sudden acceleration and rapid turns, abilities that could be very useful in a robot fish.
I see the RoboPike project as a continuation of the RoboTuna project. It's all under the same general goal of improved maneuverability and propulsion underwater. What I'm trying to solve is how do you make it swim right? If you want to turn 90 degrees, what's the right coordination for all those motors to make that happen?
John's hope is that a shoal of RoboPike would carry out search and rescue missions at sea. If robots can conquer land and sea, then surely air is the next big challenge. Conventional aerodynamics explains how birds fly, but not insects, who are also masters of the air, able to hover and turn in a flash. All of this means a real challenge if you want to create a robot which can fly like an insect. And that's the goal of a team of biologists and robot engineers at the University of California in Berkeley.
Insects do use a number of tricks that enable their wings to generate much more force than you could predict by conventional theory. What we do is actually glue the fly to a tiny steel rod, and we measure what it's doing with its wings and what aerodynamic forces it's generating, and we allow the fly to actually steer itself through a sort of virtual space. So it's sort of like letting the fly play a little video game. One of the main hurdles for building a micromechanical flying insect is to determine how the wings could generate enough force to actually stay in the air. And this has been a big puzzle for biologists interested in insect flight for many, many years, how bumblebees are able to fly. And so in order to study this problem, we've actually built a giant model of an insect flapping wing that enables us to directly measure the forces that it creates as it flaps back and forth.
It turns out that from a robotics point of view, people would rather make something that moves a little bit like this, maybe plus minus 10 degrees. But what Michael has told us is our wing has to go like plus minus 70 degrees, a very large motion. And not only that, it has to rotate plus minus 45 degrees at the same time. And so that's been a good bit of a challenge. We're hoping that we can find some shortcuts, that the fly is maybe over-designed for some of the things we want to do. So our design, we hope, will be simpler than a real fly. The final device, micromechanical flying insect, is going to look like this. It'll have a wingspan of about 2 centimeters, have some, maybe a camera in the front we can use for optical sensing to get the orientation of the device. So this is actually made of a very thin stainless steel, which has been folded up in this hollow structure. So this whole device here weighs maybe about 40 or 50 milligrams. One of the first things we would see that this being very valuable for is like in search and rescue. If there's for example, a collapsed building, something the size of this device could easily fly through small spaces and maybe find a person who's trapped.
And the flying spy could also be an artificial pollinator for plant breeders. For animals and robots alike, senses are vital for survival. Vision is particularly useful, but even the simplest vision systems are complicated to reproduce in robots. Forming an image of your surroundings is easy. The hard part is making sense of what you see. But sight is not the only solution. Bats can see using sound, and they're very good at it, so good that they can detect and catch a flying moth in total darkness. To do this, they send out pulses of sound and listen for the returning echoes. This is the basis for a robot vision system being developed at Boston University. Many robots use ultrasonic sensors to detect how far obstacles are away from them. But this system is far smarter. It's so sophisticated that it can tell one person from another by building up a waveform profile of what it sees. The operator keys in a name, and from then on the computer can recognize who or what it has sensed. And unlike humans, it never forgets a face.
Yes, Jeff is the winner. What we thought is that just as bats and dolphins use sonar to recognize objects, we could do the same thing with this sonar. So rather than just looking at the time when the sonar comes back, we look at the shape or the waveform of the entire echo, and then we decide, based on that information, what kind of object we're looking at.
Yeah, 30 and...
This system has major advantages.
Compared to a camera, the signal that is being returned by the sonar is a fairly low-dimensional signal, which means that it requires much less computational power. And another important difference is that while we may not be able to recognize color, for example, we can recognize objects on the basis of their texture, the material, and we can also do it if there's smoke or if it's dark, which is something that, of course, the camera would not be able to do.
Object recognition requires some intelligence, and so does solving a maze. So could a simple robot do this better than a mouse? The mice take a trial and error approach to the task, using their eyes and noses to guide them. If all else fails, they cheat. But eventually, they get to the food at the centre. The robot has no nose or eyes, just 3 infrared sensors to follow the walls, using them to build a map of the maze in its tiny electronic brain. But it works rationally and logically to solve the puzzle, and it knows the quickest way back out again. So which is more intelligent, the robot or the mouse? The robot is more reliable, but unlike the mouse, this is the only trick it knows. New Mexico is home to a man with novel ideas on robot design. Mark Tilden believes that robots don't need computer-based intelligence, and that they can survive in the world with simple brains made out of commonly available electronic components.
The idea is that if we could somehow build wild robots that live in our world without having to be dependent on us for batteries or power or programming, we could eventually get them up to a point where they satisfy a particular niche. Then eventually we could say, bring them back into our society and say, we want that robot to clean up our floors because after all it cleans up the junk in jungles very well, cleans up toxic waste very well. You want the abilities of, say, wild creatures, like insects. If you want to, say, throw devices into, say, the next Chernobyl and clean it up. You don't want to have to be there with a remote control or program these radioactive bugs. You never want to see them again. You just want to know that they do the task. What I've been trying to do is basically try and figure out how Mother Nature does so much with so little. And the trick is to try and see if we can actually match Mother Nature's basic principles of how to make a device that lives in the real world basically work without having to go to the complexities of computers. Many people today think that, oh, a good computer program will make the machine work. But Mother Nature has shown that good mechanics make it work. And then you add on a very simple control structure that basically fills in the necessary needs of the machine. Now, the needs in these machines are different from what you would normally expect, which is, oh, I want my robot to service me. I want it to clean my floors or rub my feet. Instead, we're trying to make robots that, like living things, live for themselves, fight for power that they need to survive, exist in the real world, last as long as they possibly can, and can take massive damage without actually falling completely apart. The world is a complex place to which we wind up instilling a bit of regularity. For example, we try and keep our floors clean, but they'll always become a little messy. Inside of a computer, on the other hand, it's a perfect world in which we try and install a bit of messy. The problem is that only rarely do the two actually meet up. And this is why, for example, computers are great when they're a single box on your desk, but they really have problems when you put them into a satellite, a Mars lander, or some other sort of device that moves around by itself, because the world is not like it is inside of a machine. And so what we've been trying to do is come up with devices based upon more complex or chaotic logic. The idea being that the better forms of controllers to handle the real world are things that think noisy, but act in a regular sort of fashion. When you can make a device which lives for years and does a task, self-contained, solar-powered, no off switch, no programming, now all of a sudden you're getting pretty close to not building a robot, but building more of a biological life form. Perhaps insects wind up looking more like robots because that's the way they are. We don't try and make robots that look like insects. Insects are actually more like the machines that we're trying to model. And it was just interesting that in our evolution of these designs, based upon engineering principles, insects just happened. And what I'm going to do now is I'm actually going to show the procedure for basically not how to build a better body, but how to build a better brain for a bug that already knows what it's doing. We just initially throw in some random components to see if their slaves will cause the front legs to behave in an appropriate manner. So building a bug on TV is one thing, but building a bug brain, this might be a first. I just have to give this thing the appropriate knowledge of which way is left, which way is right, and then hardwire it so that it basically works in the best possible way. Outside in the real world, this device is self-contained and solar-powered, so it just keeps on walking as long as there's enough sunlight. He's got a basic brain, and we can see that he's moving forward, but these legs over here don't seem to be moving in as well as these ones are. So therefore we have to change the parameters. One of the things I like to do during long summer evenings is basically just sit down with a good bug and basically build a new brain. So here we are, a walking machine without computers and without batteries that is capable of finding the light that it needs to basically stay alive.
Insects are great examples of the theory that there's strength in numbers. Take these leafcutter ants, for example. As individuals, they're tiny, they're vulnerable, with limited brain size. Each one can only carry a portion of a leaf. But as a colony, they can perform incredible feats. Well, as far as robots are concerned, maybe we could learn a bit from these. These robots look nothing like ants, but they are behaving like them.
These experiments are inspired by the social insect. What we're trying to do is to understand how we can get a lot of dumb agents, dumb robots, collectively doing something smart. What we've taken is an idea from ants, a particular type of ant called the leptothorax ant. And that ant lives in these very shallow cracks. So it can't build in 3 dimensions. It basically pushes brood and sand grains around. So it's a sort of 2D blind bulldozer. Now, what you'll find with leptothorax ants, that they're able to bring in brood and even sort it. And by extension, we're looking at that particular behavior with these robots. So the trick is, how simple can you make the commands? How simple can you make the robots in order to carry out what is quite an interesting problem, which is to sort different items?
Each robot follows just 4 rules. 1, if you bump into a robot or a wall, turn away. 2, if you bump into a disc and you're empty-handed, pick it up. 3, if you're holding a white disc and you run into another disc, drop it and turn away. 4, if you're holding a black disc and you run into another disc, back away, then drop it. And the result? A neatly sorted cluster of white discs put together by robots of very little brain. This robot knows only that its goal is to move forward. Bumping into walls impedes progress and is bad. It can detect the walls using ultrasonic sensors, and it soon learns, by trial and error, to turn before it collides with them. So how intelligent is it?
I'd say the learning robots that we have are definitely intelligent robots. They're not intelligent in the same way as humans because they simply have much fewer brain cells. Humans have something like 100 billion brain cells, whereas our robots have 50 or 100. They're about as intelligent as a slug or a snail in terms of numbers of cells. So they can't do an awful amount, but they can do things like learn. Robots definitely are intelligent. They can learn, experience the world and become individuals because of that.
Kevin has also been looking at how groups of robots can behave intelligently together despite their small brains.
With the 7 dwarf robots, we've looked quite a lot at flocking behaviour, grouping together. Essentially, they send infrared signals which tell each other, "Hi, I'm a robot, I'm here." So each of the robots know where the other robots are. A basic instinct we've put into them is to flock together, to group together where there are a lot of robots. But we've allowed for a leader to emerge. When one robot can't see any other robots anywhere nearby, it decides, I'm going to be a leader. It sends out a signal saying, hey, I'm a leader now, and off it goes in its own path. The other robots then detect there is this leadership signal knocking around, and they sort of override their initial flocking behaviour to follow the leader. We can compare how the robots behave in comparison with sheep, but also when the leadership situation, we can compare it with humans. How do humans behave? Do we select a leader? Looking at human intelligence and machine robot intelligence, they are very different things. The humans are biological form, but we think in just a limited number of dimensions, 2 or 3 dimensions, and we have a limited range of senses. With robots, it's very different. They can think in many dimensions because they have a computer-based brain, and also can have a whole load of different senses. We can look at trying to copy the senses from nature, but also we can add other ones on, such as infrared, such as ultrasonic. These are senses which robots can actually appreciate what's happening in the world around them, and their intelligence goes hand in hand with that.
The first robot toys with simple, intelligent behaviour are already on the market. The Aibo dog is the perfect pet. It won't mess up your home or need to go into kennels when you go away. More sophisticated robot toys will soon follow, and they'll behave in an increasingly lifelike way. Dave Keating works for a company that's trying to design artificial creatures with character and attitude.
If you're designing robotic toys, then what you want is to have a little bit of magic in them. They don't want to be too predictable. They want to be interesting in their behaviour. I think you want the behaviour to be kind of repeatable, but it needs to take a little while to suss out what's actually happening here. If the robot gets a little bit upset, then it will behave in a certain way because it's upset, but that's a different way that it behaves when it's happy. I think there is a big future in machines that behave in that way, simply because it's easier for us to understand and to interact with them. It's a more natural way. That's how we interact with dogs, cats, other human beings. And so it's a natural way for us to interact with machines, and I think we should strive towards making machines that are more like us.
American designers are working on this new breed of robotic toy, like this baby called Bit.
So Bits has a set of moods and emotions and drives, and it could be very compelling to interact with because of the number of different processes that are going on. You build up a very sophisticated level of complexity. You'll see that Bit can be happy if you're playing with it, but it'll tend to get kind of cranky if you ignore it, like I was doing previously. So when we were first building the insectoid robots, we noticed that kids would come up to them and they'd pet them, and this is a type of interaction we didn't expect because we were building them as better little exploring devices that could go over rough terrain, and that really got us thinking. This is compelling. There might be another direction we can take this technology in creating a new way for people to perceive and interact with machines. Because we've come so far in the past few years, our goal is to blur the lines between what people perceive as alive and what they perceive as a machine.
In the not-too-distant future, robots could be our companions from cradle to grave. This is Flo, the nurse bot. She may look after you if you can't look after yourself. She has a way to go, she's got no arms or legs, but there's still a lot she can do.
I'm alive.
Flo, hello.
Hello there. How can I help you?
Flo, what time is it?
The time is now 10 to noon in the morning.
She keeps track of appointments for you, so she can remind you to take your medication, she can remind you to go and see the doctor, and she can even do things like remind you when your relatives' birthdays are.
I am on TV right now, on Robocritters.
You could talk to your doctor through Flo, and your doctor could see, using what we call telepresence and next-generation internet technology, your doctor can see using Flo's cameras into your home, and you can have a short interview, and this could determine whether or not you need more medical help. Flo and I definitely have a love-hate relationship. She's very moody. This morning she's working reasonably well, but we've had other people come and visit the lab and try and talk to her, and she doesn't want to talk to them at all. It's not clear at all why this is. I can only decide that yes, she's a character, and she's got a definite personality, and you can really irritate her, in which case she's not going to work for you. The goal is to have people interacting with her as you would interact with another human being. How intelligent she is right now, I have no real idea, but she's on her way. Because we're all, especially working on Flo, so close to technology that we tend to think of her as more just collections of programs than a real, okay, she didn't like that, a collection of programs. So she thinks she's alive. I'm going to have to go with the robot then. Flo is not going to look like this 20 years from now, but the basic technologies are going to be there. I think that 20 years from now, people will be interacting with robots as they would with human beings on a daily basis without even thinking about it.
In Japan, they're leading the world in developing humanoid robots. You can buy this one for £29,000. Linked through a mobile phone, you could use it to do any number of jobs at home from anywhere in the world. But unlike Flo, it's not intelligent or autonomous. Honda spent $100 million getting this humanoid robot to walk and play football, but it's no Alan Shearer. This shows just how difficult it is to replicate the sophisticated combination of human senses and actions that we take for granted. Wendy has been built to have cutting-edge dexterity and coordination. She can slice a cucumber, but even this is an amazing achievement. Just think, the world's most advanced computer can carry out 100 million calculations a second, while the human brain can manage 1 million times that amount. And you then realize that robots have a long, long way to go. But the scientists are confident computers will catch up.
In the foreseeable future, every household will have their own robot, just as now every household has a car and a computer. The next technical advance will be the domestic robot, and this will be humanoid, working alongside us, like a member of the family.
So that's why they're developing a face for a humanoid robot which can express itself as we do. It follows a light, but recoils and blinks if it gets too close. It looks startled if you clap your hands, and it blushes if you stroke its head. The Japanese appear more comfortable with robots than we are in the West.
Here in Japan, we give individual robots names. Workers in the West probably think of them as mechanoid, and a threat to their jobs. But here in Japan, and maybe this is an Asian way of thinking, we treat them as equals.
Imagine how far robots may have progressed in 50 years' time. What will they look like? Will they be our servants, our partners, or our mechanoid masters?
We need devices which live with us, what we call a parallel life form with robo-ecologies, so that we can basically live in worlds where the machines basically do things invisibly for us. Given that that's the case, then the machines of the future are going to look fundamentally different from what we would expect. But if we could build things which are extremely alien, we can accept them by themselves because of the sort of things that they do for us, based upon their own abilities. That is, creating and proctoring robots in as a separate life form, rather than trying to bring them in as copies of ourselves. And that, I think, is going to be a lot more of what the future of robotics is really going to be, not some sort of android essentially making you toast. You'll always have to make your own toast. But we can actually come up with devices which would guarantee that you always get your toast exactly the same way twice. And that might be the future of technology as I see it.
I believe in the future we'll see the possibility of capturing the dynamics that we see in the animals in these new robots. And so their performance in terms of maneuverability, speed, and stability will really be striking.
At the moment, our robots are only able to cope with very simple environments, and therefore they're stupid. We, on the other hand, are able to cope with amazingly complex environments and changing environments. And that really is, I think, what makes us intelligent, or that could be a definition of intelligence.
In the future, we're going to see robots, machines that are a hell of a lot more intelligent than we are. When that occurs, they will actually be running the show rather than ourselves. So the time will come before too long that we will switch on machines that are more intelligent than we are. They will then not let us switch them off again. It's more a question of how far is that away. I would think we're looking at, 30 to 40 years, nothing more.
Perhaps the designers have got a long way to go to satisfy our vision of a robotic future. But one thing is for sure, the journey has begun. Robots, be they based on human or animal design, are destined to work among us. And they may even be the first to explore distant planets, leaving us far behind.
If the idea of robo sprint, swimming and football seems far-fetched, don't miss the final of Techno Games tomorrow evening at 6:45 here on BBC Two. And in pursuit of a healthier human lifestyle, smokers take the plunge to kick the